Mr. Tarou, in this math lesson we're going to do two examples of finding the intersection point between a line and a plane. Perfect follow-up for our video finding the angle of intersection between a line and a plane. Why don't we talk about that coordinate? We're going to do two examples, so in the description you're going to find two timestamps to jump ahead to these examples. Of course, the first one's going to start up here really quickly. You're also going to find a link to my video playlist that includes all of my lessons so far involving vectors. And if you check out my channel, you'll also find around 650 videos to date that I have covering Algebra 1 to Calc 2 all the way up to AP Statistics. So, in this example, here's what we're looking at. In 3D space, if you have a given line L in the direction of vector u and a plane pi with a normal vector of n, then, or with the normal vector, n, if vector u is perpendicular to vector n, then the line L is parallel to the plane pi, or it's actually in the plane. So there's going to be either no solution or an infinite number of solutions because every point on the line is also in the plane. Now, we know how to check this. If you have two vectors which are orthogonal, the dot product is going to be equal to 0. So before you start doing a whole bunch of math, maybe just make sure that when you pull that normal vector out, especially a nice one here where you have an equation of a plane in Cartesian format, and that takes like no time at all, take out that directional vector for your line, do the dot product, and make sure it's not already equal to 0, because then you have a special case. Otherwise, line L and plane pi are going to meet at a point, and they will in our two examples. So I'm not going to make sure that the dot product is equal to 0, because hey, I made these examples, and I know each one only has one solution. So, our first example here, find the coordinates of the point of intersection between the line x minus 2 equals y plus 1 over 2 equals 5 minus z, and the plane negative x plus 7y plus 3z is equal to 16. Now, geometrically, what's going on here? You have a big old two-dimensional plane with an infinite number of points, and while a line also has an infinite number of points, it's not quite so many, well, still infinite, but not as infinite, if you may argue. And this line, if we can identify a known point on this line with the position vector A, and then remember that we have one directional vector, vector u, for our line, if we can just start from that known point, go in this direction of vector u that has some kind of scalar multiple, all we have to find is what is that scalar multiple that we need to apply to our directional vector to, basically put the terminal point of that directional vector on or in the plane. That's going to give us our intersection point, and that's how we're going to attack this problem. Now, if I find a point that is in this plane, then when I plug in that x, y, and z coordinate, since the right-hand side is equal to a constant of 16, the left-hand side is going to equal, needs to equal, chalk down, 16, and broken. Sweet. Well, not really my chalk holder, just a piece of chalk. We're going to write out the parametric functions for this line so that we have x in terms of lambda, y in terms of lambda, or beta, or alpha, or whatever variable you're using, and then z in terms of lambda. I just showed you a shortcut way of sort of looking at a Cartesian format of a line and pulling out the known point and the directional vector, but we do want x in terms of lambda, y in terms of lambda, z in terms of lambda, so we can take those coordinates, that sort of basically that general coordinate of this line, plug it into the plane, and have an equation that's only in terms of one variable. We're going to find that lambda that makes the left-hand side equal to 16, and basically our problem is done. So we have x minus 2 is equal to lambda, therefore x is equal to 2 plus lambda. We have y plus 1 over 2 is equal to lambda, y is equal to 2 lambda, and now finally y is equal to 2 lambda minus 1. If I was talking about identifying the known point and the directional vector, I'd probably write negative 1 plus 2 lambda, but we're just going to do substitution. And we have 5 minus z is equal to lambda. We have negative z is equal to lambda minus 5. We have z is equal to 5 minus lambda. So these little equations are going to be used to substitute something in general term, the general point basically, on the line into the plane, giving us this, negative x, 2 plus lambda, plus 7 times y, which is 2 lambda minus 1. And then we've got plus 3z, so plus 3 times 5 minus lambda is equal to 16. Let's find out what lambda needs to be, the scalar multiple basically of our directional vector for the line, to make it equal to 16. So we have negative 2 minus lambda plus 14 lambda minus 7 plus 15 minus 3 lambda is equal to 16. Combine our like terms and we have negative 1, negative 4, and 14 is 10 lambda. And 15, we have negative 9 plus 15 is 6 equals 16. Subtract both sides by 6. We have 10 lambda is equal to 10, and lambda is equal to 1. Make sure that that is how I wrote this out. Now, don't get too excited. The question did not say find lambda or alpha or beta. It said find the point of intersection. So x is equal to 2 plus 1, which is 3. The y-coordinate is equal to 2 times lambda minus 1. So 2 times 1 is 2, minus 1 is 1. And then 5 minus lambda. So, of course, we have a z-coordinate of 4. And that is our point of intersection. Our last example coming up right now. It's our last example. We're going to consider the line x is equal to 2k, y is equal to 3 minus k, and z is equal to 1 minus k. We have the equation of a line here given to us in parametric form. And the equation of our plane vector r is equal to 4 minus 2 alpha plus beta times vector I plus 2 minus beta, or you might think of this as 2 plus 0 alpha minus beta times vector j, and 2 minus alpha minus 3 beta times vector k. We're going to write down the parametric equations for plane pi, and then here's where we have to shift our skill set and look at this at a different angle than the previous example. Hence, we have to use the parametric equations we set up in A to answer the question, basically, what's the intersection point? We can't go fall back into Cartesian format or basically make this question look more like our first example. If we don't use the parametric equations that are describing plane pi to answer part B, we're not going to get any credit for our work. Okay, so how are we going to do that? This is kind of a funky way of writing the equation of our plane in vector form. So what I'm going to do is remind us that vector r is a position vector for a general point in the plane, and pull out this information that we're looking at some constants. We're looking at some coefficients of alpha. Here we have negative 2, 0, and negative 1, and we have some coefficients of beta. So basically, I'm going to write this vector form for the equation of a plane not as a sum of component vectors, but as our vectors written in column component form. So we're going to have vector r is equal to x, y, and z, and pull out that known point for this plane. That's going to be our coordinates that don't have basically a scalar multiple applied to it. So we're looking at a known point of 4, 2, and 2. And then we're going to write a directional vector that's in the, basically has the scalar multiple of alpha. So here, and we're going I, j, and k, so we're going top-down component vector in the terms of the component vector in the direction of the x-axis I, y-axis j, and z-axis k. Negative 2 is getting multiplied by alpha. 0, we have no alpha here, so it had to be multiplied by 0. And then we have a multiple here of alpha of -1. So if you think about taking the scalar multiple, -2 alpha plus 0 alpha minus alpha showing up right here as our coefficients of I, j, and k. And then we've got our other non-collinear directional vector for our plane, the coefficients of beta, which are 1, -1, and -2. Now here we can easily see that our three parametric equations are going to be x is equal to 4 minus 2 alpha plus beta, y is equal to 2 plus 0 alpha. I'm going to go ahead and write that 0 for teaching purposes, minus beta, and z is equal to 2 minus alpha minus 2 beta. And if you look up here, you can see that information falling into our parametric form. I'm just doing this rewrite for ease of teaching, and honestly, it helps me too not to make any kind of careless mistakes. And let's just make sure that I haven't made one. I say careless. I try really hard not to make them, especially when teaching. And yet for me, I'm just very prone to doing that. Forget a negative, or 2 plus 2 is 5. It's so annoying. And then I can't find my own mistakes, but I can find a student's mistake in like 2 seconds. We're going to have to use these three parametric equations to find the intersection point between the line and the plane. And it's still basically going to be a system of equations like we did in the previous example. It's just going to have to work out a bit more complicated because of the word hence saying I have to use these. So how can I bring together information about the plane and information about the line? Well, it's going to be just like we did before, through the variables of x, y, and z. So x is equal to 2k, which is now 4 minus 2 alpha, except I keep writing alpha. And y, well, the y coordinate for this line, the general y coordinate, is 3 minus k. Copy the rest of this down. 2 plus 0 alpha minus beta, and z, substituting in our value or expression of 1 minus k equals 2 minus alpha minus 2 beta. So we have three equations with three unknowns: k, alpha, and beta, k, alpha, and beta, k, alpha, and beta. Of course, we had sort of the same thing here. Well, no, we didn't. We have 1, 2, 3, 4, 5 unknowns. So now we have basically a system of equations. And we're going to rewrite this so that we have all of our constants on one side and all of our variables on the other. So maybe we bring over, let's write this as add and subtract. So we're looking at 2 alpha minus beta plus 2k is equal to 4. And bringing over this is going to be 0 alpha plus beta. We already have the k on the left-hand side, so minus k. And 2 minus 3 is -1. Add alpha. So positive, add 2 beta. Get a minus k. And that's equal to 2. Okay, now that's a minus k, so we're going to do 2 minus 1, which is equal to 1. Now, here is where you need to look at this and go, how do I want to attack solving this problem? And there's all kinds of ways you have of solving a three-equation, three-variable system. I'm going to put links to other lessons, and it just depends on the math that you're in. You could do Guassian elimination, like maybe you're taking this course inside of a you're looking at this topic inside of a linear algebra course, where you're studying Guassian elimination and working through these systems through row reduction type thing. You could look at setting up a bunch of determinants and using Cramer's rule. Have a link to that lesson as well. Or you can be working with matrices. Now, if we let matrix A, and what I'm going to do is I'm going to talk through this process and just conclude the video and say we're done. But I'm also going to set up the camera on to probably my TI-84 and show you how to work out these calculator commands, because this is going to be a question when my kids take their test. This is a calculator question. So they're going to be allowed to use one of two operations in their calculator to get this answer. And one is with matrices. So we can set up matrix A as being the coefficients of 2, -1, 2, and 0, 1, -1, 1, 2, and -1. And then matrix B is going to be equal to our constants, which are 4, -1, 1. Now, what we have here is that I can write this left side of this 3x3 system as this matrix times basically another 3x1 matrix of x, y, or I was going to say x, y, and z, but alpha, beta, and k. And that would look like this. Making sure I don't run out of room here. Matrix A times a 3x1 matrix of, first variable was alpha, then beta, then k, and that is equal to our constant matrix of, well, I can write 4, -1, 1, but I'm already using a variable here, so I'm going to say that this is equal to matrix B. Now what you want to do is you want to get rid of this, you want to move this matrix A away from these three unknowns by multiplying both sides by an inverse, right? Like if you have x squared equals 16, you apply the inverse math operation to both sides, you square root. If you have the sine of theta equals 1/2, that's on the unit circle, so you should know what the answer is, but to solve that equation, you would get the theta angle measure out of sine by applying the inverse sine to both sides. Well, here you want to apply the inverse matrix to both sides, and we're going to have this matrix of alpha, beta, and k is equal to the inverse of matrix A. Now now this is another way. We have Guassian elimination. You could use Cramer's rule, and you could use like a matrix equation situation. Find the inverse of this 3x3 matrix. I have a math lesson on that too. I'll put a link in the description if you have to do this by hand. Find that inverse matrix and then multiply it to B, and then get your answers. It'll be a 3x1 matrix, which will be in sequence of alpha, beta, and k. And even quicker than that, maybe, what you could do is you can set up, since I'm already using sort of identifications of A, matrix A and B, you can find more room and set up matrix C as, and you're going to set up a 3-row, 4-column matrix, 2, -1, 2, and 4. There's no way of putting like sort of an augmented matrix into your calculator, but you can just go straight across and have our coefficient of alpha, beta, k, and our constant. And then same with the second row, 0, 1, -1, and -1, 1, 2, -1, and 1. And then with this in your calculator, I'm writing lots of numbers and stuff here, so let's just one more time. Here we go, good. Now go into the matrix menu of your calculator and ask for a reduced row echelon form of this matrix. And what it's going to spit out is a matrix that looks like this. And I want to just look at this and make sure that I know the correct three answers. We're going to have 1, 0, 0, 0. Our second row is going to be 0, 1, 0, and 2. And then 0, 0, 1, and then 3. And basically what I mentioned about initially, you can solve this 3 by 3 system by the Guassian elimination in that reduced row echelon format. The calculator's doing that for you. And we have that, well, alpha is equal to 0, beta, because that's the next variable in our column there, is equal to 2, and k is equal to 3. Now we can go back up here and say that looking at the equation of our line, now that we know that k is equal to 3, we can look at the equation of our line and say x is equal to 2 times 3, which is 6, y is equal to 3 minus k, 3 minus 3, which is 0, and z is equal to 1 minus k, which is negative 2, and get your coordinate, your point of intersection is 6, 0, negative 2. And you can also, I don't know why you'd want to, because we're done, but maybe if you want to double check your work here, and I'm just double checking mine as well, you can take alpha and beta, alpha of 0 and beta of 2, plug those variables into our parametric form for the coordinate of a point on the plane. And when you plug in alpha was 0 and beta was equal to 2, of course, if you've done everything right, you're going to get the same coordinates of your point. So hold on so you can see how you put this into your calculator quickly and where those commands are in your calculator. But otherwise, I'm done. I'm Mr. True. Bam! Go to your homework. I don't normally record like this, so I hope this comes out clear enough, but we're going to go matrix A. We're going to edit it, and we're going to put in that 3 by 3 matrix, which was 2, negative 1, 2, 0, 1, negative 1. These are the coefficients that were on alpha, beta, and k. Last row, 1, 2, negative 1. I'm going to second quit to get out of this, and then we're going to put in second matrix B, which is 3 rows and 1 column. That's not what I meant to do. I want to edit matrix B and put in that 3 by 1 matrix, which was 4, negative 1, and 1. Second quit. Now remember, we had matrix A times our 3 by 1 matrix of alpha, beta, k was equal to the 3 by 1 matrix of 4, negative 1, 4. If I multiply the inverse matrix to both sides, and this is how I'm going to do that, I want to do the inverse of matrix A times matrix B. So I'm going to go second matrix, choose A, and then I'm going to put on an exponent of negative 1, asking the calculator for the inverse of that matrix, and multiply that by matrix B. And there's my answers for, let's see, alpha, beta, k, which was 0, 2, and 3, like you saw in the video. Or I can go second matrix. Let's do matrix C and edit that. We're going to set up a 3-row, 4-column matrix. Now this time I'm going to include the constants at the end. So we have 2, negative 1, 2, and 4, 0, 1, negative 1, and negative 1, and 1, 2, negative 1, and 1. Now, another alternative way again of finding alpha, beta, k is to quit this, go into the matrix menu, do math, and you want a reduced row echelon form with matrix C. And there you go. That's how you use your calculator. To couple of ways. There's many more. Again, you could use determinants and Cramer's rule or just do this by hand, but that is how you find and solve quickly a 3 unknown, 3 equation system with your graphing calculator. One more time, I'm Mr. Taru. Bam! Go do your homework.